Okay, good morning, good afternoon, good evening. So, welcome to our online lesson, and in this video, we are going to focus on revising for MA 110. So, we'll be revising for MA 110 even as we look forward for the upcoming test 1 coming ahead. So, revising our MA 110. So, I'll look at a number of questions, meaning that it will be more like Changanya questions which we are going to be using throughout in this video. So I'll see how long this video might be. It means I might make another one, so we'll see how far we can go with this one, and then we can be able to cut it and make the other one next. Okay, so I'm sure my screen is visible to everyone. So what I'm going to do is I'll just be following through certain questions just to help you revise and be able to remember something as you're preparing for your MA 110 test 1. So this is MA 110 class. So this is test 1 revisions. So I'll start with the first question, which we are going to look at this morning. So the first question will be let f of x be equal to x plus 1 over 2 squared minus 1 over 4, and let g of x be equal to 1 over the root of x. So these are two functions given. Let f of x be that and let f g of x be that. So in this question you are being told to find g of f of x and also determine the domain of the function. So this is the first question we're going to start with. So if we let f of x be equals to that function, and we also let g of x be equal to that function, so in that functions given, find g of f of x and also determine the domain of that given functions. So what are we having here? What are the key concepts that you have to understand from this question? What are the key concepts you have to understand from this question? Number one, we are looking for g of f of x. So these are composite functions. I'm sure we can remember what composite functions are. Composite functions, so with just what we know under composite functions, is that we have to understand that when it comes to composite functions, these are functions composed of each other. So this is a composition. So this is a composition of two or more functions. So it means that in a certain given function, we are able to replace one function and slot it into another. So this means that if I'm talking about g of f of x, it means in the function g is the function which is starting, and in the function g, we are slotting inside a new function f. So it means g is evaluated at the point when x is equals to f of x. So that is why this is just as good as in the function g of x, after the x, we slot in f of x. So it means it's an evaluation which we tend to have there. But in a situation where we have f of g of x, this means we are standing in f, and in the function f, can you go ahead and replace a new function called g of x. So this means I'm going to have the function f and slotting in the new function g of x. So it means this is a function composed, this is a function we are composing f composed with g. So this is what we call f composed with g, and this is what we call g composed with f. It means in g we are inserting f of x. Here it means in f we are inserting g of x. So in the same given functions here, if I'm looking for g of f of x, it means that I'm looking at in g inserting f of x. So this is just as good as saying in the function g, can you go ahead and slot in the function f of x? That's what it means. So upper x by default will evaluate it at the point when that x is equals to f of x. That's the concept you're going to use there. But we know what g of x is. So remember, what is g of x? G of x is equals to 1 over root x. And what is f of x? F of x is equals to x plus 1 over 2 squared minus 1 over 4. This is what we have there. So if this is the case number, we just use the same values which we have and begin to compose them. So I'm going to start. So I'm looking for g of f of x. So in the function g we are putting in f of x. So it means this is just as good as 1 over upper x in the function g, we are slotting in f of x. So what does this mean? This is just as good as 1 over the root of x plus 1 over 2 squared minus 1 over 4. So this is the function we are calling to be g of f of x. So it's a function g composed with what? With f. So in the function g, we are slotting in g of, in the function g, we are slotting in f of x. So even whatever is happening, if you want to, if you wish to, you could have simplified this into another simplest function. So we can simplify this further by simply saying this 1 over something. You can just be able to simplify what is in the bracket, this is in the root here, or in the first place you could have simplified f of x. Whatever you feel like doing is the same thing. So look at this. If we look at this f of x was written as x plus 1 over 2 squared minus 1 over 4. But this is just written in terms of the standard form of a certain quadratic expression, trying to look at it in terms of the turning points, the intercept and the like. So this can still be written as the usual quadratic form which you always know. But this is a quadratic function. It means we're able to expand this function to be in a simplified version, which I think 3/4 of us tend to understand. So how does that work? I can break these two to be 2 parts. It means x plus 1 over 2 squared can still be written as x plus 1 over 2 multiplied by another x plus 1 over 2. I'm just trying to break it down in a version which we are able to simplify. There is a minus 1 over 4 there. So if this is the case, how is this going to be? I'm now going to have x times everything there. This will be x squared, and this will be plus x over 2 this times that, it will be plus x over 2 this times that, it will be plus 1 over 4. So just breaking everything, x times everything, at the same time 1 over 2 times everything. That is why we have this expanded version. But remember, there is a minus 1 over 4 outside. That's what we have. So obviously, even from the 1 over 4 and 1 over 4, this is a 0. It means the simplified version of this just becomes x squared 1 over 2 plus 1 over 2 is just as good as 1. So it means we have a variable x, so this is just as good as x. So 1 over 2x plus 1 over 2x. So this is half. Half x plus half x will give us 1 complete x. So it means the simplified version of this quadratic function f of x is as good as x squared plus x. So it's the one which I can even replace in there to come up with my final g of x. So we say that g of f of x. We say that g of f of x is a function, we are saying 1 over the root of the f of x. Since g of x is 1 over x, so this becomes 1 over the root of x squared plus x. This becomes a simplified version of the composite function g of f of x. As simple as that. So that's the first part. But remember, we have the second part here where you are being told to find the domain of this function. What is the domain of the function? Remember, what did we say about the domain? The domain is a set. The domain is a set of input values. The domain is the set of input values that defines a given function. That defines a given function. So if this is our given function, we're looking at the input values, and in this case the input values, what are we talking about when it comes to input values? We're talking about x values. That's what it means by input values. Then the range talks about the set of output values that defines a given function. So obviously when we look at the range, in this case, the range is a set of output values. Output values that defines a given function. A given function. And in this case, we're talking about y values when it comes to the range. So a set, it means it should be a collection of values. So if I look at g of f of x, how is this g of f of x going to be defined? With the values of x. That's the set which we are looking for. We are trying to collect that set. So what did we say when coming to find the domain? So we said that when determining the domain or determining the domain, always look at the restrictions of the function. Yeah, this is the restrictions. Yeah, how do you spell restrictions? Restrictions in the function. So you should always look at the restrictions in the function. These restrictions might be as follows. Number 1, if the function has a denominator. If the function has a denominator. If the function has a denominator, for example, e.g., where you have f of x to be equals to, maybe let's say 3x plus 1 over 2, maybe let's say x plus 1 as well. So this is a certain function given, and then you're being told to say find the domain of the function. So the restriction here is the denominator. So if there is an expression of x, there is an expression of x in the denominator. Here I can see an expression of x. I can see a polynomial there in the denominator. I can see an expression of x there. So the expression there in the denominator is our restriction which we are going to use when coming up with a domain. Remember, the domain should be input values, values of x. So if I was to collect the input values which are defined in this function, what are those values? So the expression of x in this denominator is what is going to give me a restriction of the function. So if I see a denominator there, the task is that tell yourself that the denominator should not be 0. This is how you will find your domain in that function. Remember, this numerator has no effect. Any value of x you can insert here, the numerator will be defined, it's okay. But if whatsoever we put in the denominator and the denominator becomes 0, this whole expression will become undefined. So that is why for this function f of x to make sense, our denominator must not be 0. So it means our focus will be on that guy who is in the denominator. It means that x plus 1 should not be equal to 0. So it means this implies that x should not be equal to what? -1. This when 1 goes to the other side. So if I had this function here, what could be my domain? My domain can be any value of x except for -1. So it means my domain here could have just been x being all real numbers but except -1. That's what it means. And I can write this as x is a member of all numbers, all real numbers. Obviously will run from -infinity. But when I reach -1, I have to jump that value. I'll use round bracket. Union from -1 to +infinity. This is another way of representing it. So this is my domain. The focus is in the denominator. That denominator should not be 0. So when you're looking at the restriction, the first restriction you can look at is the denominator. Do you have an expression of x in the denominator? If yes, equate that thing not to be equal to 0. The other thing, or the second restriction you can also talk about for now, is you having an even root. If the function has an even root, so if the function has an even root, what happens? We are going to have a situation where, for example, let me have f of x to be equals to the root of x plus 1. This has an even root. Obviously, even means the index of the root is even. Maybe it's a square root, a fourth root, a sixth root, eighth root, etc. So if the function has an even root, what we are being told here is that the domain of this function, when I'm looking for the domain of this function, my focus should be the expression in the root. So we look at the expression in the root. So even if this function was f of x equals to another thing outside here, maybe I can set plus 2x outside. I don't care about this 2x, because this 2x has not any restriction. This 2x we can accommodate any values of x and it will still be valid. But for the guy in the root, we have certain limitations. Remember, if I have a negative expression in the root, this becomes imaginary or complex. So for this function to be defined, it means it's supposed to be real. So for this function to be real, we're talking about what is under the root. What is under the root should not be negative. And I'm sure if we say not negative, we know what it means. It means it can be 0 or positive value. That is why the domain of that function is going to be found from the restriction which we are saying x plus 1 should be greater than or equal to 0. Hence implying that x will be greater than or equal to -1 becomes our domain of this function. That's what it means. So these are the two restrictions which you have to focus on. And remember, if there are no denominators, there are no square root, it means the function becomes all real numbers. If there is no root or no denominator. You don't know if the Chizungu sounds nice there. So if there is no a root or no denominator, just know to say the domain is all real numbers. That's one thing you have to understand. That's the concept which is there. So now, obviously there will be other restrictions which we will look at later on when it comes to exponential functions and logarithmic functions for the domain. For the domain of a function, there will be those restrictions. But for now, let's go back to our question. What did we find as our g of f of x? Our g of f of x was 1 over x squared plus x under the root. So what restriction are we following here? We are following the denominator. I can see an expression in the denominator. This implies that for this function to be defined, the root of x squared plus x should not be what? 0. But it's not the only thing, and we have the square root. So if I look at the restriction of the denominator, it means whatever I have in the denominator here, whatever I have here should not be 0. But if I look at the restriction of the root, it means that anything under the root should not be negative. It means it can be greater than or equal to what? 0. Those are the two restrictions we are going to be looking at. So it can either the case of greater than or equal to 0, or it can be a situation of x squared, or this should not be equal to 0. That's what we are being told there. So it means the intersection here which we're talking about, which one is non-can? We can solve for this, but we can also solve for this. The answer for this and the answer for this should be intersected for this function to be defined. So we'll solve for both cases, and for both cases the answer needs to be intersected so that things make sense. Because if we solve for this, what am I going to have? I'm going to have a situation whereby if we square both sides here, this is a radical equation. If we square both sides, we're just going to have a situation where we just have x squared plus x not 0. And this is quadratic, we can factorize x plus 1 should not be equal to what? 0. Implying that x cannot be 0 or x cannot be what? Cannot be equal to negative 1, because when this guy is equal to 0, 1 will go to the other side, becomes x not equal to negative 1. These are the first case in the first restriction there. What about the other side? This is an inequality, and we know how to solve inequalities, and in most cases if this is a greater than symbol, we know that it is going to turn into the outside non-can. Remember inequalities, how do you solve quadratic inequalities? So in solving this quadratic inequality, this is as good as x plus 1 is greater than or equal to 0, and the critical points are, when we solve this, the critical values are x equal to 0 and x equal to negative 1 in this equation. So when you are solving an inequality, we can, when finding the critical values, assume this to be an equation. So it means x is equal to 0 and x is equal to negative 1 will be our critical values, so that we can do our testing from there. So the testing will be when x is 0 and when x is negative 1, and we use those factors. So the factors is x, so I can draw my cosine table there, or my sine graph, where I'll have factors here. So I'll have x at my first factor, the other factor is x plus 1, and the last thing which I'm going to have will be the over, which is a product, x times that. So the product, which is x open bracket x plus 1, so that when I do the testing we can see what is happening from there. So if this is the case, we have -1, 0, and so forth. So what you can do is you can have those columns and distribute them according to ascending order. Distribute this on these lines according to ascending orders on the number line. We know that between 0 and -1, the biggest value is 0. So it means -1 can be there and 0 can be there. So it means if we're looking at the number line, this line we can act as, this can act as negative infinity and this can act as positive infinity. So that we do some testing there. So in the testing, what are we doing? In between here, negative infinity and -1, you choose any value as long as it's in between. So that value you're choosing, you're talking about a value which is less than -1. Maybe you can say let x be equals to -2, because -2 is less than -1. Here, any value between -1 and 0, you can say let x be equals to what? 0.5. Obviously that's the half. Here, any value greater than 0, you can say let x be equals to 1. So these are the values we're going to test in there. So when x is -2, what will be the outcome of this? Obviously, this is a sine graph. You're just concerned with signs. What is going to happen? This will be more like -2. This is -2 there. 1 minus -2. This is as good as what? 1 minus -2. This will be -1. -1 times -2, it will be positive. So the answer will be positive there. Sorry. Let me do this. I'm talking about the overall number. So this is an answer from the overall. Let me do this. Okay. So we're saying the value of x. Remember, it's this value is inserted in this. So if x is equal to -2, the answer is a negative value. If x is equal to -2 in this expression, to be 1 minus -2, the answer will still be what? Negative. Then later on number, the product is the outcome at x and outcome at x plus 1. So negative times negative, the answer should be a positive in the overall. We'll go to the same when it comes to -0.5. -0.5 here, the answer is still a negative. -0.5 here, to be 1 minus 0.5 to be a positive. It means negative and positive, it is a negative in there. Which is +1 here, it is +1. Positive there, it is a positive. Positive times positive is positive. We're just concerned with positive, what is the signs, so that you can be able to test what values, or maybe what will be the solution for this. Will it be a solution between -infinity to -1, or -1 to 0, or 0 to positive infinity? That's the concept. So with this situation here, what am I going to have? I can now go ahead and test to say, look, go back to your inequality. Inequality says this answer should be greater than or equal to 0. Your answer is coming in the last row where the overall is, the product is. So ask yourself, which column satisfies a greater than 0? So in the last column here, the overall is positive. Is it true that any positive number is greater than 0? Obviously it is true. This is a yes. Is it true that a negative number is greater than 0? This is a wrong column to look for. Is it true that a positive number is greater than 0? Yes. So it means that from your testing, you can see that if we have x plus 1 greater than or equal to 0, the solution should be x is a member of from -infinity to -1 in the first column here. Now, in this case, it is also greater than or equal to, so it means it will have a square bracket. Union, the outside part, which is 0 to positive infinity. Open, closed. So this is the solution for the inequality we've used. And the solution for the other solution which we had was x should not be equal to 0 or x should not be equal to -1. So remember, what is happening? We'll have to intersect these two solutions. So in the other side, we said x should not be 0 or x should not be equal to -1. And the solution this side is x has everything from -infinity to -1, but at the same time from 0 to +infinity. What does this mean? So if you look at these two solutions, their intersection, it means the solution we're going to pick should satisfy both the cases. That's what we are talking about. So that's why we're looking at, if I look at this solution here on the number line, if I was to draw a number line here, if I was to draw a number line, what is going to happen? Talking about this from -infinity, the number line, obviously we know the real number line is running from -infinity to +infinity. Oops. To +infinity. Okay. So to +infinity there. So what is happening? When I look at this, obviously there need to be a -1 somewhere, and I need to have a 0 somewhere. So this means x should not be 0 or x should not be -1. It means if I'm coming from -infinity this side, when I reach at -1, I have to jump this point. It will be an open bulb. When I continue, when I reach at 0, I have to jump this guy. It should be an open bulb. And then I can continue to +infinity. This is the solution which we are talking about, which is sketched there. So this thing sketched here is, oops, I don't know what's happening to the screen. So this thing which is sketched there is, let me change some color so that you can see what is happening. So this is what is sketched there. Number, I want to sketch this. What does this mean? This means from -infinity to -1. So if I'm coming from -infinity there, when I reach -1, it is also included, we shade, but at the same time we jump. We don't include the in-between values. We start from 0 again, we go to the positive part. That's what it means. So if this is the case, then you ask yourself to say, okay, what is the intersection where the upper lines, where the upper set and the lower set are intersecting from? That's the solution. And you can see that the intersection is only happening from -1 to infinity and from +0 to infinity there, as you can see. So that's where we are going to base our solution from. So from -that to that. So it means the domain of the function which we are talking about is just as good as x being a member of from -infinity to -1. But is -1 going to have a square bracket or round bracket? Here it is shaded, here it is open. It means it should be open, because here it is not included, there it is included. -1 is not an intersection. So we jump this part. This is not an intersection, because that part is not included, here is included. So this part is not an intersection. This is union 0, +infinity. Is 0 going to be square or round? Here it is shaded, here it is open, so it means it's supposed to be round. So this becomes the domain of their composite function we are talking about, and we are done. So that's the first question. which we are just trying to revise there on composite function, as well as trying to determine the domain of that function. And I think you also can also have an insight from this question that we are able to remind even ourselves on how to solve quadratic inequalities as we are solving for the domain. Yeah, okay. So now let's go to the second question for today. Let's go to the second question for today. Let me change some colors again. Go back to black. I think black is better. So second question, you can use question number 2 there. You say question number 2. So we're going to say that a binary operation star is defined on a set of real numbers as follows. So as follows, and therefore as follows is as follows. So A star B will be equal to A over B squared, where A and B are members of the real number set. So where A and B are members of the real number set. That's what I've been told there. So this is the statement where I've been told a binary operation star is defined on set of real numbers, which is as follows. A star B should be equal to A over B squared, where A and B are members of the real number set. So what is the question in this case? We are being told to say, number 1, is the operation, defined on the set of real numbers. Is the operation defined on the set of real numbers? That's a question. And then you can also give a reason. So I'm sure we can recall binary operations. So I think we mentioned last time when we were doing something to say, when it comes to binary operations, what is binary operation? This is just an operation which involves 2 numbers at a go. That's what it means. So the type of operation which involves 2 numbers at a go. And we know when it comes to operations, obviously we're talking about a summation, multiplication, division, addition, those things. So when we're performing those operations, according to binary operation, is that we're being told to say we can only perform that operation using 2 terms at a go. 2 terms at a go. So that's the concept which we are using there. So number, with binary operation, we're trying to use the concept as well of closure rule, where we are having an understanding that if this is an operation which we are defining here, A star B is the type of operation we're saying we're trying to operate 2 numbers A and B. So in the operation here, we can simply perform this operation by using this statement. So we're simply saying that if this is defined, what is going to happen is that if we perform A star B equals to this expression, if A and B are in the set real numbers, if A and B are in the set of real numbers, even the outcome after the operation, this also should also be contained in the set of real numbers. That's the concept. So this also should also be contained in the set of real numbers. If this fails to be contained in a set of real numbers, the outcome is failed to contained in the set of real numbers. It means this operation is not closed on real number set. So it can only be closed if the elements are coming from that set, as well as the product or maybe the outcome should also belong to that particular set. That's what we mentioned. I think you can remember and follow out the document on binary operation. We sent you a document on that. I think we also talked about something. So that's what we have. So now the question comes in to say, is the operation defined on the set of real numbers? So we just have to confirm the closure property there. So we'll have to confirm the closure property. So we are saying A star B is equals to A over B squared, where A and B are members of the what? The real number set. So this operation will be defined if A over B squared is also contained in the real number set. If that is true, then it is going to be defined on a set of real numbers. If this fails, maybe it is failing now, but it can be defined on another set and not real numbers. So how do we check that? We look at an observation between A and B squared. So we're saying, since A and B are members of the real number set, we can have a situation where B is equal to 0, and we know that 0 is also part of the what? Of the real number set. So we're trying to see a certain case, or try to think to say, is there a situation where this thing which we're going to have cannot exist in the real number set? That's what we're trying to look at. So in this operation, we can have a situation where B is equal to 0. Obviously, this is in the number set. We know that 0 is in the real number set. So when you can have a situation where B is equal to 0, being what? Members of what? The members of what? The real number set. So what is going to happen if B is equal to 0 in this case? Hence, the operation becomes undefined. So if B is equal to 0 in the denominator, this is a fraction. So if B is equal to 0, it means the whole expression becomes undefined. So the reason why this function, or maybe this operation, is not defined on real number set, because there exists a B equal to 0 in the real number set, making the operation to be what? Undefined. Such that, let's say, if we have A star B, and then where we're saying A is equals to B squared, where B is equals to 0, we'll have A star 0 to be equals to 0 over 0 squared, which is equals to undefined. And if this is undefined, this implies that A star B equals to A over B squared is not defined on real numbers, and you're done. So this is not defined on real numbers because the products, they exist a certain case where the outcome is not part of the set. Now let's go back to the second part on the same question, but I want us to solve this time around. On the same question, we're trying to solve a question which says, is the operation star commutative? Is the operation star commutative? If not, give a counter example. And for sure, this can only be proven using a counter example. So, what we are going to have there, by commutative property, what does it mean? So if we say talk about commutativity, this means A star B should be equals to B star A. If this is true, then the operation is commutative. So the commutative property, this is the commutative property which we are talking about. So the order here does not matter. If I start with A star B, the answer should be the same as B star A. So if the two answers are not the same, then we can conclude that the operation is not commutative. That's what we are saying. So we want to show that, we want to check if A star B is equals to B star A. That's what we want to check. So we can start by maybe trying to use a certain counter example. Let's maybe using a counter example. You say let A maybe be equals to 1 and also B be equals to maybe 2. Then what are we going to have? A star B, which is equals to A over B squared. This is going to be equal to what? This would be 1 star 2, which is going to give us 1 over 2 squared, which is going to give us 1 over 4. This is the first part. Then we want to show the other part, which we are calling to be B star A. B star A means B over A squared. B over A squared. And this implies that B, remember, is 2. So this is 2 star 1. And this becomes 2 over 1 squared. And the answer becomes equal to what? Equals to 2. Now, confirm if the two answers are correct. So, we can see that A star B is not the same as B star A. Here we have 1 over 4 not equal to 2. Hence, A star B equals to A over B squared is not commutative. We are done. Is not commutative. And we are done. That's what we have there. And then the last part of this question says, the last part of this question is going to say, can you evaluate now? Evaluate -1 star open bracket 1 star 2 plus -1 star 1 star 2. Can you evaluate this situation? That's what you are being told. So now let's try to evaluate. Remember, we are still using the same operation. The operation is A star B is equals to A over B squared. That's the operation. So we can maybe first compute what? Let's try to compute A star 2 there, and then we can just come and replace everything. So in this situation we can say, okay, what is it? Okay, let's try to be replacing step by step. We have -1 star 1 star 2 plus -1 star 1 star 2. This is going to be equals to negative 1 star. So from the operation which we are using here, the first number is more like a, so this becomes 1 over 2 squared, plus this number is a, this becomes negative 1 over 1 squared, star 2. And then from there we continue. This is going to be equals to negative 1 star 1 over 4 plus this and that. This becomes negative 1 divided by 1. That's obviously just as good as what? This is just as good as negative 1 star 2. That's what we have there. So it means the next thing number I can work on is this part, this operation, negative 1 star that. So this is a and this is b. So this becomes negative 1 over 1 over 4 squared, plus this is a, this is b, negative 1 over 2 squared. So what am I going to have? This is negative 1 over 16 plus negative 1 over 4. So from there, what am I going to have? I'm now going to have this divided by that. Obviously we can know that this is just as good as, am I correct? Yeah, this is just as good as negative 1 divided by that. Obviously you can perform your mathematics there. Negative 1 divided by, maybe take it to grade 1 way for people not to get confused. We're talking about this case, plus negative 1 over 4. Obviously we know now that when you're talking about division of fraction, this will reciprocate, this changes to multiplication. The answer becomes negative 16 here, plus the answer becomes negative 1 over 4. So that when we say this is over 1, the lowest common denominator is 4. This into 4 is 4 times 16. I think that should be 60. Is it 64? Negative 64. 4 into 4, 1 times that, that's negative 1. So that the answer becomes negative 65 over 4 as the final solution evaluated. So that's the answer we are going to have there. So let me end here in this video, because the video is about almost an hour now, 53 minutes. So I think let me end it here so that we can meet in the next revision video. Thank you very much and have a flavored week.